Remember, we talked about operations as being a combination of projects and processes in the real world in most companies. Excuse me. And so let's talk about delays for either reason. And you'll see that this is intimately tied to the discussion we just had in terms of process capacity analysis. Okay. So first, let's look at project delays, and then let's look at process delays. Okay. So, what is a project? A project is nothing but a sequence of tasks or a set of interconnected tasks. And for every project, just like for every process, there's a bottleneck. For every project, there's a critical path. So, the critical path is the equivalent concept to a bottleneck for a process. So, that's what we call a critical path. And so, now what is a critical path? Here's how we define it. It's the sequence of tasks that constrain the time to complete the project. Okay, so in other words, and so here, this particular sequence of tasks, that's what we call the critical path. That now tells us the minimum time to complete the project. In other words, the project at least has to take time equal to the time along the critical path. And so we'll see an example of this that will illustrate this concept perfectly clearly. And so why do we care about the critical path? Because any delay on any of the tasks on the critical path will imply a delay for the project. So even 1 minute or 1 day of delay on any of these tasks will essentially imply a delay in the overall project. And so therefore, capacity and resources are first devoted to the critical paths. Now, there could be several critical paths, just like you could have several bottlenecks. If two steps in your process have the same capacity, then both of them, and they have the minimum capacity, then both of them will be the bottlenecks. Similarly, in this case, if you have two paths that take the same amount of time to complete, and they are the longest paths in the project, then again, both of them would be critical. So again, so how do you identify a critical path? Find the longest path through the project. That's your critical path. So now, which are your critical tasks? Any task that's on any critical path, that's a critical task. So which means what? If you have even one task that you identify on a critical path, a delay of 1 minute or 1 day on the task is going to imply a delay in the project. And so how do you then handle resource allocation? So you would often divert resources from tasks that are not critical, in other words, those that have some slack, to tasks that are critical. And right, and so when you do those resource transfers, sometimes you might end up creating new critical paths. Just like when you take resources from non-bottleneck tasks and apply them to bottleneck tasks or bottleneck steps, the tasks that were previously not the bottleneck could end up being the bottleneck. Okay, so similarly here, the same concept applies here. And project critical paths are not that easy to determine all the time. So, I mean, of course, you have standard algorithms that can help you do it, but visually, it may not be so easy to figure out. So let's take a simple example. And so let's write out this example in Excel, and so we can actually see this. So here are my tasks. Suppose this is a design process, and you first are developing the concept, you're designing the item or the product, you're acquiring the resources to develop or to manufacture the product, you're developing the prototype, you're testing the prototype, you're refining the prototype, and then you're releasing, or you're waiting for the release approval, or essentially the approval stage. That's what we call the release approval step. Okay, and so rather than write out the elaborate description of the task or the name of the task, we will just provide symbols. So you have A, B, C, D, E, F, and G. Okay, so these are your tasks. And now, how do you define the relationships here? So let me actually save this here, and let's call it project and process delays. Okay. And how do we now define the relationship between the tasks? We have what's known as the predecessors relationship or successor. Predecessor. Okay. So we have what's known as the precedence, and therefore the succession relationship, okay, or the successor relationship. And so what does this indicate? And so by the way, when I say predecessor, I'm taking some license. These are actually immediate predecessors. So how do you know A is the start task? That's the first task because it does not have any predecessor. Now B has A as a predecessor. C also has A as a predecessor. And D has B as a predecessor, and E has C and D as a predecessor. Okay, and also similarly, F has C and D as a predecessor, and G has E and F as predecessors. Okay, so this is your relationship between the tasks. These are the sum total of all the immediate relationship between the tasks. Okay, now based on this, you can of course draw the diagram. So more on that in the next slide. But first, let's capture the time. How much time in days does it take for each of these tasks? And so here A takes 21 days, 5, 7, 2, 5, 8, and 2. Okay. And now let's look at the network. So here's the network. So A is the start task, takes 21 days. B and C both have A as their predecessor. Okay, so what does that mean? You cannot start B, you cannot start C unless you complete A. So this is a finish to start relationship. Okay. Now the next step is let's say D. Now D has B as a predecessor. D takes 2 days to complete. And now, why would you need to define E first? Because now if you look at E, E has both C and D as predecessors. Okay, which means what? If you have two predecessors, you cannot start E until you finish both C and D. Cannot start E until you finish both C and D. And so this is again a finish to start, and you have to wait until you finish C, or depending on which one you finish first, you have to wait to complete the other task as well in order to start E. Okay? Same thing with F. So you have to wait until you both finish C and D before you can start F. And then G, you have to wait until you finish both E and F before you can start G. Okay. And so now, what's the critical path? And how long is this project going to take? What is the delay in completing the project? Delay here meaning not delay in the sense that certain tasks are late. No. Delay meaning what is the lead time for the project? How long from start to finish? That's the context I'm using the word delay. Okay, and so critical path, remember, is the longest path. So you can list out all the paths here. So what are my paths? So you can see here one path is A, B, D, E, and G. Okay. Another path is A, B, D, F, and G. Third path is A, C, E, G. And a fourth path is A, C, F, and G. Okay. Now let's list out how much time each of these paths is going to take. So A, B, D, E, G takes 21 plus 5 plus 2 plus 5 plus 2. Okay, that's how much it takes. A, B, D, F, and G takes 38 days. Similarly, A, C, E, G takes 35 days, and A, C, F, and G takes 38 days. Okay. So notice these four paths take this amount of time to complete. Now, here's the critical, or here's the most important concept. What is the critical path? Critical path is obviously the longest path. Now, why is that? And so why does the project take that much amount of time to complete? It's not like you have a choice that I can complete this path, A, B, D, E, G, or I can complete this path, A, B, D, F, G, and then I'm done with my project. No. You have to complete all tasks before you can complete the project. In other words, You must have completed all the paths in the project in order to complete the project. You must complete all the paths. And therefore, now notice some of these paths are parallel. So what is the critical path, or what is the completion time first, let's say. Completion time for the project, that is equals the maximum of the completion time across these critical paths. So let's put it this way, project completion time, and that is 38 days. And what is the critical path, or what are the critical paths? It's the paths that take the longest time. And so here you have two critical paths. Here's a critical path, and here's another critical path. Okay, and what are my critical tasks? Any task that's on any critical path, that's critical. So if you notice, the only task that is not critical, that's not on any critical path, is actually E. Notice E is not on this critical path, E is not on this critical. A is on both of them, B is on one, C is on one, D is on one, F is on both, and G is on both. Okay, the only task that's not critical is E. All other tasks are critical. Okay, and so this is the simplistic way to figure out what the critical path is. Okay, and so you have two critical paths. And so notice the only task that is not critical is the one that would have slack. Okay, and so that task is E. And you can easily see here from a simple visual analysis, you could see what's the difference between a critical and non-critical path is the task E. And so now if you take the difference, that's how much slack E would have. If you take the difference between this critical path and this non-critical path, so the difference is task E versus F. And so now if you take the difference in the time, you can see that E would have a slack of 3 days. Same thing here. ACEG, the difference between ACFG and ACEG is 3 days. And the only difference is because now you're replacing a critical task with a non-critical. And so essentially you have 3 extra days you can take to complete task E. That's called the slack for task E. Okay? Now, what if there are more tasks than just these 7? And so it's not just more tasks. What if you have more dense relationships? In other words, right, you have many, many paths that you can take to complete, right, or to go from start to finish. And so you need a more robust approach. So here's the robust approach. So we would do this in 2 passes. We would do this using what's known as the forward pass and the backward pass. Okay? So in the forward pass, we calculate the earliest finish, okay? Let's start with earliest start rather, and then the earliest finish. Then you would calculate the latest start and the latest finish. Okay, so these are the 4 parameters you would calculate. So in the forward pass, you would calculate the earliest start and the earliest finish. And in the backward pass, you would calculate the latest start and latest finish. Okay, and so that's the principle. So let's go ahead and do that. Okay. All right. And so first up, how do you start the algorithm here, the forward pass? You start from the start task, which doesn't have any predecessor. So you would start from A. And then by convention, you would say the earliest you could start A is time 0. Okay? Now, once you know when you can start it at the earliest, if you now look at the task time, that's the earliest you could finish it. So 0 plus 21 days. And this relationship is always true. No matter what the earliest start time is of any task, the earliest you can finish it now in a simple, right, for the lack of any other information, is just the earliest start plus however long it takes for you to complete the task. And so now you would take this relation, you take this relationship or this equation, earliest finish equals earliest start plus the task time all the way down. Now, the only thing that remains to be computed are the earliest start times rather, based on these predecessor relationship. Okay, that's what we have to figure out in the forward pass. Now, let's look at task B. So what is the earliest you can start task B? Remember, because of the predecessor relationship, you cannot start task B before you complete task A, which means the earliest you can start it is the earliest finish for task A. Hopefully I can make this slightly bigger for now. There you go. And so the earliest you can start task B is the earliest you can finish task A. Okay, and what's the earliest you can start task C? Similarly, C has A as a predecessor, and so that would be the earliest finish for task A. Similarly, D, what's the earliest you can start D is the earliest you can finish B, and so that would be, be B, not earliest you can finish B, which is 26, okay, because D has B as a predecessor. Now, E, if you notice, has two predecessors, C and D. So what's the earliest you can start it? You have to wait until you finish both, which means the earliest you can start it is the maximum of C and D, because you have to wait. In this case, you're lucky because both of them take the same earliest time to finish. So your earliest start time for E would also be 28. And similarly for F, it's the maximum of the earliest finish times for C and D. And so that would be the earliest you can start task F. And then finally for G, it has two predecessors, E and F. And so this would be the maximum of 33 and 36, which means the earliest you can start G is you have to wait for F to finish. And so that would take you 36 days. And so the earliest you can start it is 36. And so now, what is my earliest finish time for task G, which is the completion of the project? The completion time is now equals the earliest finish time. Okay, the earliest finish time for the project. That's how soon I can complete it. Okay. All right. So this is the forward pass. Now it's pretty simple. And why is this more robust? Because notice you're only performing two computations for every task. Whereas as the number of tasks grows, as the number of relationships between the tasks grows, you can have the number of paths growing exponentially in the number of tasks. And so the previous method, where you're just listing out all these critical paths, that could be incredibly inefficient as the number of tasks is growing. And so in this approach, though, right, this is the critical path approach, or right, the critical path method, also called the CPM method. This algorithm, you just have to do two computations per task. And so no matter how many tasks you have, you just have to compute 2 times per node or per task. And so this is actually linear growth in the computational effort. And so that makes it much easier, okay, much more manageable. This is the kind of algorithm people should design, where the effort actually increases linearly in the number of inputs, or the number of tasks in this case. If it grows exponentially or if it grows as a squared or a cube, that's not as robust. That's not as efficient. Okay, and so here's the forward pass. Now let's do the backward pass. So right, the backward pass, we start from the latest finish for the last task. By convention, we say that's equals. It may not be. Sometimes customers want you to finish it. Latest finish talks about what does the customer want. Earliest finish talks about what's feasible, technically feasible for us, right, as project managers. And so latest finish, suppose the customer says, okay, the earliest you can do is 38, but then I actually want it on day 35. It's possible. Or they can say, listen, I'm not ready to take ownership of this product, or of this, I'm not ready to start manufacturing this product yet. And so now I'm willing to wait until day 40. Okay, that's when I'm really able to start manufacturing. So you can take a couple of extra days to finish the project, in which case all the tasks will end up having some slack. Okay, so so suppose by convention, for now, let's just keep it equal to my earliest finish. In fact, I'm not going to hard code it. I'm going to say equals the earliest finish. Okay. And then what is my latest start? Just the same way. Remember, earliest finish was earliest start plus the task time. Latest start is the latest finish minus the task time. Okay. And so now this relationship is always going to be true. Okay. And so now all we have to do is calculate the latest finish for each of these tasks based on the successor relationship or predecessor or successor. Anytime you have a predecessor, you automatically have the successor relationship as well. Okay, so we'll use that fact here. So now, what is the latest finish for task F? If you look at the diagram, let's look at the simple diagram here. So what is the latest I have to finish F by? Remember, the latest I have to start G by is 36, which means what? F has only one successor, which is G, so I'm looking at that successor here. And my latest finish is equal to the latest start for that successor, which means I have to absolutely finish F no later than day 36 because G is waiting on me. Because the latest I can start G, or the latest I have to start G is by day 36. Okay. Similarly, E has only one successor, which is G. Latest finish for a predecessor, if that predecessor has only one successor, then it's equal to the latest start of its successor. Now, what's the story with D? Now, D has two successors. D has one successor F and one successor E. And so what is the latest finish for that task, D? It's now the minimum. So I absolutely have to start it by the latest start time of one of my successors. Okay, so in this case, this would be, let's see here. So this, if I can write it better, and there you go, E and F. E and F are my successors. So I actually have to start it based on the sooner of the latest start times of E or F. Okay, so the earlier of the latest start times. So therefore, I'm using the function minimum. So notice here now, F has to start at the latest by 28, and E has to start at the latest by 31. And so what's the latest I can finish D by, or I have to finish D by? Now that would depend on which of these latest start times comes earlier. So because F, I have to start it by day 28, I have to absolutely finish D by 28 because F is waiting on me. Okay, if I can't do that, then the entire project will slip. And now let's look at C. C has again two successors, E and F. So again, this is the minimum of E and F. Again, 28. And then now B has only one successor. So this is now the latest start for its successor D. And now A has two successors. So it's going to be the minimum of the latest start time for B and C, which is the same, 21 days. And so this is the picture. Okay. So why do we care about doing the backward pass? We already figured out what's the earliest finish time for the project. That's the completion time. So the reason we want to do this is so we can calculate what's known as slack. This is what this step is designed to do, the backward pass. Okay, and make this slightly smaller so I can adjust it. Okay, and so what's my slack? My slack, I can either define it as latest finish minus earliest finish, or I can also define it as latest start minus earliest start. Let me do latest finish minus earliest finish. So 21 days minus 21. If they are the same, there's no slack. Okay, and so notice all the tasks, none of the tasks have any slack except for task E. Okay, and so this is how I can calculate slack. So the forward pass helps me estimate the project completion time. The backward pass helps me calculate the slack. Okay, and so this is called the forward backward pass algorithm or the critical path method. Okay, now how can I identify the critical path? Based on the slack information. So here's how I can do it. I have to start from the first task that doesn't have any slack, in this case A, and I have to find a way to the finish, but in a way that I'm not increasing the slack. Remember, critical tasks don't have any slack, and a critical path is nothing but a sequence of critical tasks. And so let me start from A and try to go to G without encountering any slack. So how can I do this? I can go from A, I can go to B. So notice B, if you go back and look at the diagram, so I can go to B. B does not have any slack, so I take B. And I can now go to, right, let's do this one step at a time. And now from B, I can only go to D. And by the way, that's allowable because D does not have any slack. And from D, think about it, I can either go to E or F, but E has slack. So I'm not allowed to include E. That's not critical. Critical path only has critical tasks. And so the only way I can go to G is through F, and then I go to G. Okay, so that's a critical path. The other way I can do it is I can start from A. Without encountering any slack, I can go to C. Now from C, I can go to E or F, but because E has slack, I'm not allowed to go to E. I can only go to F and G. Okay, so that's also a critical path. Okay, and so this is how you would identify the critical paths once you calculate the slack. Try to go from start to finish without encountering any slack, and you cycle through it until you've actually encountered all the tasks that are critical. Okay, so that means you've identified all the critical paths. All right, so this is the forward-backward pass algorithm in order to figure out project delays and how much slack you have, okay, for any given task. Now notice if my latest finish is now earlier, it's now 35 days. So notice there's actually negative slack, which means some tasks have become even more critical. And even task E is now become critical. So I have no wiggle room. Okay, that's because my latest finish is now earlier than my earliest finish. So which means now I have to work double quick, or I have to work much faster in order to complete the project. Okay. All right, very good. So this is how we would look at estimating project delays and looking at the impact of critical tasks and looking at the impact of right, customer requirements. What's the latest start? What's the latest finish versus the earliest finish, and so on. All right, so this is the critical path method. Okay, so now let's talk about processes. How do you estimate? So this is project delays or completion time. Let's just call it completion time in case the word delay is confusing. And so project completion times and critical path.